Okay, so this section we're going to talk about patterns, the periodic law, and the periodic table. So, we got this periodic table on the wall. Where did it come from? Well, back in 1869, Dmitri Mendeleev noticed that certain elements had repeating properties. And so he put the elements in order of increasing mass and found that these properties reoccurred in a periodic manner. So here, if you look at the first 20 elements and put them in order, we see that lithium and sodium and potassium all have similar characteristics. They're metals, they're highly reactive, etc. And if we look at, beryllium and magnesium and calcium, they also have very similar properties. And so the periodic law is a summary of these observations. When the elements are arranged in order of increasing mass, certain sets of properties recur periodically. It's a little bit like a piano keyboard, right? Where you've got middle C, and then you go through the other keys, and then you get to the C that's an octave above, right? And it's kind of the same note, but it isn't the same note, right? So that's kind of what this was like. So instead of just having a long list like that, he arranged them so that the elements that had similar properties were on top of each other in more of a grid form. So the vertical columns, these three elements have a lot of similar characteristics. These guys have similar characteristics. Now, back in 1869, there were a lot of elements that hadn't been discovered yet. So he left gaps in the table and actually predicted that elements would be found to fill in those gaps, and he even predicted their properties. So this is just kind of interesting. This periodic table shows when things were discovered. So all of these in the lighter yellow, those have been discovered since 1950. But there were a bunch that were missing even during Mendeleev's time. Anybody still know what Tetris is? The game? Yeah. Little giggle or anything? Just a smile? This is a joke. This is how in 1869 Dmitri Mendeleev completed the first periodic table.
By playing Tetris?
It looks like it could be a game of Tetris, doesn't it?
Well, no, because there's no Tetris. The lines are filled, but there's nothing going away.
Oh, well.
I don't know, it looked pretty Tetris-y to me, man.
Yeah, I just want to rotate that thing before it falls down, right?
Yeah.
You've got this guy coming in for a landing.
It falls and the properties of those elements just magically change.
So he was looking at ordering things in terms of increasing mass, but now we know that the correct ordering is by atomic number, the number of protons. And most of those correspond the same, but there's a couple of examples where they're different. So if we look on the periodic table, we can find one. So number 52 and number 53, right? So tellurium has a mass of 127.6, and iodine number 53 is 126.9. So it's a higher atomic number, but a lower mass. So Mendeleev, did not switch those. He did switch them. He took them out of order of mass because he recognized the properties didn't line up, but he didn't know why. So later, when the proton was discovered, then we realized what the difference is there. So there are many parts of the periodic table. You could think of this as chemistry's best cheat sheet, right? There's just like so much stuff hidden in there. And the more you study chemistry, the more you learn about what's hiding in the periodic table. But there's some major divisions. So this periodic table has all of the metals in this, light yellow, kind of beigey color, off-white color. So all of these are considered metals. There's a little key up here. And the green ones are nonmetals, and we see these guys are all grouped up here, except for helium. And then the metalloids, hydrogen, except for hydrogen. The metalloids are in between the metals and the nonmetals. We've got some numbers on the sides here, numbering the rows. Those are called periods. And we have some numbers at the top that are numbering the columns or the groups. So this periodic table has two sets of numbers, and so does the one on the wall. The one with the A's and B's, that is the numbering system that most people in the United States use. And just numbering 1 through 18 is what most of the rest of the world uses. Since we're in the U.S., I like to use the U.S. version. So metals, nonmetals, and metalloids, we should have a general idea of what makes these different. So metals are good conductors. They'll conduct heat and electricity. They're malleable and ductile, which means malleable means if you hit it with a hammer, it's just going to dent, and you can bang on it and smash it out into a flat sheet. You can't do that with everything. Ductile means you can pull it into a wire. Metals are often shiny, tend to lose electrons when they undergo chemical changes. And that's the most important feature for our purposes. They tend to lose electrons. The nonmetals are kind of the same properties of metals, but opposite, because these are the not metals, right? So metals are good conductors, nonmetals are poor conductors. They are not ductile, they're not malleable, and they gain electrons when they undergo chemical changes. And then we've got the metalloids, or the semi-metals. Some of these are also called semiconductors. Their properties are between metals and nonmetals. So they conduct electricity, but not very well. And all of their properties are just kind of in between. So here we have the group numbers clearly identified. These are the periods. And then we talk about the main group elements and the transition elements. So here in the yellow, these two columns and these guys over here, those make up the main group elements. And the pieces, the things in the middle here are called transition elements. Being a little creative, and you think about this as being one side of a riverbank, and this is the other side of the riverbank, and this is kind of a sand color, and here's the river in between. This is the between, it's a transition, right? So main group, transition element. So you should be able, just using a periodic table, to identify whether an element is a metal or a nonmetal, whether it's a main group or transition element. You should be able to identify its atomic number, its group number, and its period number. It's all written out there on the periodic table. So some of these groups have names. Group 8A, these are called the noble gases. So those guys on the far right. These are mostly unreactive. The alkali metals are group 1. Those are metals, as is kind of obvious here, and they're all very reactive. Right next to them are the alkaline earth metals, group 2A, not quite as reactive. And the other named group is the halogens over in group 7A, right next to the noble gases. So the main group metals tend to lose electrons to form cations that have the same number of electrons as the nearest noble gas. And I'll explain that with the periodic table in a minute. It comes down to this. They form cations. The charge is equal to the group number. That's if you use the group 1A, 2A, 3A numbers. Main group nonmetals tend to gain electrons. They're going to form anions then. And they're also going to have the same number of electrons as the nearest noble gas. So one way to remember this is these form anions, and the charge is equal to the group number -8. The transition elements are not very predictable. Okay, so here we have part of the periodic table. So over here in group 1A, hydrogen is not an alkali metal because it's not a metal, but the rest of these guys are alkali metals. They all form a +1 charge when they make an ion. They are in group 1. Group 1 makes a +1. Here, group 2 makes a +2. Aluminum is also in the main group. These guys are transition. Aluminum is also in the main group, forms a 3+. It's in group 3. So how is this equal to the electrons of the noble gases? So if we look at sodium here, can't tell on this periodic table, but on that one we see that sodium is element number 11. That means it has 11 protons and 11 electrons, right? So if sodium loses an electron, now it has 10 electrons. Well, what element has 10 electrons? It's neon. Neon has 10 protons and 10 electrons. So I kind of think of this as being like the noble gases are like the in-group in high school. They're the group that everybody wants to, they want to get into that group. So one way that teenagers often try to fit in is by dressing like everybody else, right? I'm expressing my individuality by dressing like everyone else at my school. So I think of the electrons. Electrons are on the outside of the atom, right? The protons are on the inside. They're kind of like your personality, your soul, who you are, right? Can't change that. But you can change how you look. And atoms can change the number of electrons they have by becoming ions. So what sodium is doing, sodium's like 11 electrons. This is not a cool look, right? The cool kids are wearing 10 electrons. That's this guy over here. So if he loses an electron, then on the outside, he looks like neon. Does he become neon? No. He's sodium with a +1 charge, but he looks like neon, right? So that's what they're doing. Magnesium has a +2 charge because to get to the same number of electrons as neon, it has to lose 2 electrons. Aluminum would lose 3 electrons. Now, why doesn't this do that? Well, this would have to lose 4 electrons, and that's just a little too much. So let's look at the nonmetals, these guys over here. The nonmetals also want to have the same number of electrons as the nearest noble gas. But fluorine would have to lose 7 electrons. It's like cutting off your arm. It's just not going to happen to get down to helium. So it's going to go to the closest one, gaining 1 electron. So fluorine had 9 electrons, and it gains 1 to form an ion. Now it has the same number of electrons as neon. The number of protons didn't change, though, so it doesn't become neon. So you need to be able to predict the charges of these elements when they form ions. So metals, the main group metals, group 1 +1, group 2 +2, group 3 +3. That's pretty good. So these guys. Now the book says group number -8. That's true. This is group number 5. 5 minus 8 is -3. That's not very fun. So I think of this as being maybe like a board game, right? And we're going to start at the noble gas, and we're going to count backwards till we get to the nonmetal that we're interested in. So if I want to look at nitrogen, this is -1, -2, -3. It's 3 squares over from the nearest noble gas, so that tells me it needs 3 extra electrons. It has a -3 charge. So selenium, we're going to start counting here. This is 0. Those don't make electrons. They don't make electrons. They have electrons. They don't make ions. Start here at 0, -1, -2. All of these guys can form -1 ions. All of these -2, and these guys -3. Why is carbon not on here? Well, for carbon to form an anion, it would have to gain 4 electrons to form a cation, it would have to lose 4 electrons. It's like stuck in the middle. And it's like, it's just too hard. And so carbon's one of those kids that's like, you know what? Forget them. I'm just going to be myself, right? I'm not going to try to be like these other people. I'm just going to rock who I am. So that's what happens to these guys in the middle. They just really don't form ions. Any questions? So predict the charges of the monoatomic ions formed by these main group elements. And this monoatomic just means mono is one atomic atom. So these are one atom ions. So just nitrogen. What charge is nitrogen going to have? -3. Because we're going to start, here's nitrogen, and we're going to start over here, -1, -2, -3. So the charge for nitrogen is -3. If we're going to write the symbol for the ion, we're going to write the element symbol, and we're going to write the charge as a superscript with the number first and the sign after. So that's the nitrogen ion. What about rubidium? +1, because it's in group 1. Okay, so that has a +1 charge, and the symbol would be rubidium with just a plus sign. Because chemists don't like to write the number 1 unless they have to. Any questions?